Well, let me ask you something. And perhaps just let it settle in your mind for a moment. What if the place you call home, this quiet, familiar spiral of stars we call the Milky Way, is not, sitting in an ordinary part of the universe at all? What if, you see, we are, well, drifting inside an immense cosmic emptiness, a vast void, billions of light years across, where matter itself is scarce, and gravity itself, whispers more softly than elsewhere. When we look up at the night sky, it feels full, packed with stars, galaxies, light. And yet, that's the curious thing about the universe. On the largest scales, it's not smooth, not evenly spread. It's more like a delicate cosmic foam, filaments and walls of galaxies surrounding enormous regions of near nothingness. And recent observations, from powerful surveys and space telescopes like James Webb, suggest something quietly unsettling. Our galaxy may lie inside one of these gigantic voids, a place where the universe is thinner than average. And that's the thing. If our position is unusual, if it really is, then some of our deepest cosmic puzzles, why the universe seems to expand at conflicting rates, why distant galaxies move the way they do, why ancient quasars appear where they shouldn't, might not be mysteries of physics at all. They might be questions of location, questions of perspective, not just what the universe is doing, but where we are when we measure it. You know, science isn't just about equations and data points. It's not just numbers on a page. It's a human story, a slow realization of where we stand, in a universe that is vast beyond intuition. And tonight, I'd like you to gently drift into that realization with me as we explore what it truly means to exist inside a cosmic void. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And as you're listening, perhaps notice where you are right now, the quiet around you, the rhythm of your breath, and let the universe slowly expand in your imagination. It's always fascinating to see who's joining us from all around the world. So let's continue. Before we talk about where we are, we have to talk about what the universe actually looks like. And that's the thing. You see, for a very long time, we imagined space as mostly empty. A vast, dark stage with galaxies sprinkled through it like distant lanterns. That image is comforting, simple, almost poetic. But it's wrong. Or at least, it's incomplete. And, when you look closely enough, when you let the universe speak in its own language, a very different picture begins to emerge. Because the universe, it isn't smooth. It isn't evenly filled. It's not a gentle mist of matter spread uniformly in all directions. Instead, it's clumpy. It's textured. It's structured in a way that feels almost organic. Not just random chaos, but also not perfect order. Something in between. And that middle ground is where the story really begins. When we map the positions of galaxies across hundreds of millions, even billions of light years, what we see is extraordinary. Galaxies gather together. They cluster. They cling to one another under the quiet pull of gravity. They form long, luminous strands called filaments, stretching across space like cosmic highways. These filaments intersect at dense nodes, massive clusters where thousands of galaxies swarm together, bound in slow, graceful motion. And between them, between all these glowing threads and knots, there are enormous regions with very little inside them at all. Voids and, the name is almost misleading. Because a void isn't truly empty. It's not nothing. It's more like a whisper compared to a shout. A region where matter is sparse, where galaxies are few and far between, where gravity has gently evacuated material over cosmic time. The universe, you see, behaves a bit like rising bread dough. Some parts become dense and chewy, others stretch thin and airy. And that's not a metaphor pulled from nowhere. It's a consequence of physics, of gravity amplifying tiny differences that were present at the very beginning. That's the astonishing part. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. Almost. The differences were tiny, fluctuations so small they barely register. But gravity is patient. Gravity doesn't need urgency. Given enough time, even the slightest imbalance becomes dramatic. Regions with a little more matter pull in more, growing denser. Regions with a little less matter lose out, becoming emptier and emptier. And so, over billions of years, the universe sculpts itself into this vast, foamy structure. We call it the cosmic web. And it really does resemble foam, not just poetically, but geometrically. Thin walls of galaxies surround great bubbles of emptiness. Filaments trace the edges, clusters sit at the corners, and voids dominate the volume. Most of the universe by volume is void. That's something worth pausing on. Most of existence, most of space itself, is defined not by what is there, but by what is not. And, when you think about that, it shifts something inside you. We tend to focus on the bright things, the stars, the galaxies, the explosions, and the light. But the universe is shaped just as much by absence as by presence, by emptiness as much as by matter. It's not just what gathers together that matters, but also what is pushed apart. Voids, then, are not mistakes. They're not gaps waiting to be filled. They are a natural outcome of cosmic evolution. In fact, you could say they are inevitable. If gravity is allowed to act on an expanding universe with even the smallest initial irregularities, voids must form. They are as fundamental as stars or galaxies. And that realization is quietly profound. Because for a long time, cosmology worked under an assumption that, on the largest scales, the universe looks the same everywhere. Homogeneous, isotropic, smooth when averaged over large enough distances. And in a broad statistical sense, that's still true. But the details matter. The details always matter. And when you zoom in just enough, not too far, but not too close, you see that structure dominates. Foam dominates. Emptiness dominates. And, there's another layer to this. Voids are not static. They evolve. As the universe expands, voids expand faster than denser regions. Gravity pulls matter out of them, not into them. Galaxies near the edges of voids drift away from the center, sliding down gentle gravitational slopes toward filaments and clusters. So voids grow. They become emptier, larger, more influential over time. You might think of them as passive, as irrelevant because they contain so little. But that would be a mistake. A void exerts influence not by what it holds, but by what it lacks. A lack of gravity is still a gravitational effect. And that absence shapes the motion of galaxies, the flow of matter, the way light travels across the cosmos. So, when we say the universe is foamy, we're not just describing a pretty pattern. We're describing a dynamic system, a living architecture written in gravity and time. And within that architecture, voids are the dominant feature. They are the background against which everything else stands out. And, Perhaps this is where it becomes personal. Because we are observers, we are inside this structure, not hovering above it. We look out from a particular place, from a particular environment, shaped by local conditions. And it's tempting, very tempting, to assume that our location is typical, that where we are is average, ordinary, unremarkable. But what if it isn't? That question, doesn't come out of philosophy alone. It comes out of observation. As our surveys of the universe have grown deeper and wider, as our telescopes have mapped galaxies farther and more precisely, hints have emerged that our cosmic neighborhood may be unusual, that the region of space we inhabit might be less dense than average, that we might be living not in a crowded metropolis of galaxies, but in a comparatively quiet suburb, or even something more extreme, a void. And, well, before we rush ahead, it's important to understand that voids come in many sizes. Some are relatively small, tens of millions of light years across. Others are enormous, spanning hundreds of millions or more. They overlap, they merge, they nest within one another like bubbles in foam. There is no sharp boundary, no sudden edge where density drops to zero. It's all gradual, all statistical, all beautifully messy. Which is why studying voids is so challenging. You don't point a telescope at a void and see nothing. You see fewer galaxies. You see patterns in what is missing. And that requires patience, data, and a willingness to listen to what the universe is telling you, even when it whispers instead of shouts. And, there's something deeply humbling about that. We often celebrate the triumphs of astronomy when we discover something new and bright. A new planet, a new star, a spectacular explosion. But here, the discovery lies in recognizing emptiness, in understanding that what isn't there can be just as informative as what is. It's not just out there, you see. It's also in here, in our assumptions, in the quiet frameworks we use to interpret the cosmos. Voids challenge us because they force us to confront the possibility that our measurements, our conclusions, our sense of cosmic normality might be biased by where we happen to be. And that's the deeper thread running beneath this chapter. Not just the description of structure, but the implication of perspective. We grow older, clocks tick, civilizations rise and fall, all within a tiny corner of a universe shaped on scales almost beyond comprehension. And yet, from that corner, we try to infer the whole. So, when we talk about the cosmic web, about filaments and clusters and vast empty regions, we're not merely cataloging structures. We're setting the stage. We're acknowledging that the universe has texture, that it has neighborhoods, that it has environments. And once you accept that, once you truly let it sink in, another question naturally follows. What kind of environment do we live in? And, if the universe is mostly void, and if voids influence expansion, motion, and measurement, then perhaps our place within one matters more than we once thought. Perhaps some of the puzzles that trouble modern cosmology are not signs that our theories are broken, but hints that our address in the universe is a little unusual. That idea doesn't diminish the beauty of the cosmos. If anything, it deepens it. It reminds us that understanding the universe is not just about equations and data, but about context. About knowing where you stand when you look up at the night sky. And as we begin to ask whether our galaxy, our local group, our cosmic home sits inside a vast region of emptiness, we find ourselves drawn gently, inevitably, toward a much more specific and much more unsettling possibility, one that invites us to look closer at our own cosmic neighborhood and ask, quietly but insistently, what kind of void we might actually be living in. And so, standing at the edge of that thought, the idea that emptiness itself might shape everything we see, we begin to wonder something quietly unsettling. Not about the universe in general, but about us, about here, about this particular patch of space-time from which we are asking all these questions. Because once you accept that the universe has structure, real structure, not just smooth averages, then you have to face the possibility that where you are matters. And, that's where things become, well, strange. For decades, astronomers assumed that the Milky Way lived in a fairly typical region of the cosmos. Not special, not privileged, just another spiral galaxy drifting along in the grand average of everything. That assumption was comforting. It fit neatly with a philosophical instinct, the Copernican idea that we are not at the center, not unique, not unusual. And most of the time, that instinct serves us well. But science, you see, doesn't exist to comfort us. It exists to test even our most cherished assumptions. And, when astronomers began to count galaxies carefully, methodically, in every direction, something curious emerged. The farther they looked, the more they expected the number of galaxies to increase smoothly with distance. More volume means more galaxies. Simple, elegant. But that's not exactly what they found. Instead, there was a subtle but persistent deficit. Nearby, relatively speaking, there were fewer galaxies than the cosmic average would predict. At first, it was easy to dismiss. Cosmic variance, perhaps. Measurement uncertainty. Dust. Selection effects. The universe is messy after all. But as surveys improved, as data accumulated, as independent teams repeated the analysis, the pattern remained. And, that pattern had a shape. A vast one. We now call it the KBC void, named after the astronomers who brought it into focus. A region of space roughly 2 billion light-years across, centered more or less on our location, where the density of galaxies is significantly lower than average. Not empty, never empty, but underdense enough to matter. Large enough to matter. And that scale is hard to truly grasp. 2 billion light-years. Light itself, racing at the ultimate speed limit of the universe, takes 2 billion years to cross it. Our entire evolutionary history as a species fits comfortably inside that span. The rise and fall of civilizations, the slow shaping of continents, the blinking on and off of countless generations of stars, all of it happens while a single photon makes its way from one side of this region to the other. And, the unsettling implication is this. The Milky Way doesn't just happen to be near a void. It appears to be inside one. Near the center, no less. And that is not what you would expect if all locations in the universe were truly equivalent. It's not that the idea violates physics outright. Voids of this size are rare, but rarity is not impossibility. In a universe as large as ours, rare things do happen, somewhere. The question is not whether such a void can exist, but whether it makes sense that we are inside it. Whether it challenges the assumption that our cosmic address is unremarkable. And, well, the evidence comes not from a single observation, but from many threads woven together. Galaxy redshift surveys, measurements of luminosity density, the way brightness accumulates with distance. Again and again, the data suggest a local universe that is less crowded, less massive, less gravitationally rich than the regions beyond. And that difference has consequences. Because gravity, you see, cares about density. It cares deeply. In denser regions, expansion slows more. In emptier regions, expansion speeds up. It's not that space itself behaves differently by choice, but that the distribution of matter tells space-time how to curve, how to stretch, how to flow. And if we live in a region with less matter, then the local expansion of space around us will be slightly faster than the cosmic average. Not just a little curiosity, but something measurable. Something that could quietly influence our interpretation of the universe. And, when you think about how we measure cosmic expansion, you begin to see the tension forming. We measure distances to nearby galaxies. We measure their speeds. We build a relationship between how far away something is and how fast it appears to be receding. That relationship is our window onto the expansion history of the universe. But it assumes, perhaps unconsciously, that our local region is representative of the whole. If it's not, if we are sitting in an underdense bubble, then the nearby universe would appear to expand faster than it truly does on average. And, that realization is not trivial. It ripples outward, touching some of the deepest puzzles in modern cosmology. But even before we get there, there is something almost poetic about the idea itself, that our cosmic home might be quieter, calmer, less crowded than most places. That the night sky we see, rich though it is, might actually be sparse by universal standards. It's not just out there, you see. It's also in here. In the way our environment has shaped what we observe, what we infer, what we think is normal. And, this doesn't mean the universe is conspiring to fool us. There's no malice in it. It's simply geometry and gravity playing out over unimaginable spans of time. But it does mean we have to be careful, because when you live inside something, especially something enormous, it's very hard to see its full shape. Think about standing inside a vast fog bank. From within, everything looks the same in all directions. Only when you move far enough, or gather enough perspectives, does the structure reveal itself. And the KBC void is like that. Too large to perceive directly, but subtle enough to leave fingerprints on our measurements. And, there's another aspect to this that's easy to overlook. The galaxies inside voids are different. On average, they are less disturbed, less battered by collisions and mergers. They tend to retain their gas longer. They form stars more gently, more steadily. The Milky Way, with its graceful spiral arms and relatively calm history, fits that profile rather well. That doesn't prove anything by itself, of course, but science rarely hinges on a single fact. It's the convergence that matters. The way independent lines of evidence lean, ever so slightly, in the same direction. And, if we accept, even tentatively, that we live inside such a vast underdensity, then the Copernican principle doesn't vanish. It softens. It becomes statistical rather than absolute. We are not at the center of the universe. We are not special in any mystical sense, but we may not be perfectly typical either. And perhaps that's not a failure of cosmology, but a refinement of it. Because the universe, is not obligated to make our lives simple. It doesn't promise that every observer will see the same thing from every vantage point. It only promises that the underlying laws are the same. Gravity works the same everywhere. Light behaves the same everywhere. But initial conditions, distributions, environments, they vary. And that variability is where richness comes from. So, the idea of the KBC void invites us to reconsider something subtle but profound, that our measurements of the universe are local acts, that when we infer global truths, we are extrapolating from a particular place, a particular moment, a particular cosmic neighborhood. And most of the time, that's fine. But occasionally, the universe reminds us to check our footing. And, Perhaps this is why the notion has gained traction in recent years, especially as data has improved around 2025. Not because it overturns everything, but because it offers a coherent way to connect several loose threads. It's not a wild speculation pulled from thin air. It's grounded in observation, in careful accounting of what we see and what we don't. And yet, it remains controversial. As it should. Extraordinary claims demand extraordinary scrutiny. Some argue that such a large void centered on us strains probability. Others suggest alternative explanations, subtle biases, unknown systematics. And that debate is healthy. It's the sound of science thinking out loud. But even amid disagreement, one thing is clear. The question itself is unavoidable now. We can no longer assume without checking that our region of the universe is average. We have to test it, measure it, challenge it. And, once you start down that path, once you allow for the possibility that our cosmic home is underdense, you open the door to deeper implications. Because if local structure can influence expansion measurements, then it might help explain why different methods of measuring the universe don't quite agree. Why the cosmos seems to tell slightly different stories depending on how and where we listen. And that tension, quietly simmering beneath the surface of modern cosmology, is where this story naturally wants to go next. Toward objects so bright they can be seen across the universe, toward the early epochs of cosmic history, and toward observations that seem, at first glance, to exist in isolation. Quasars, blazing alone in unexpected places, whispering hints that our picture of the early universe may be incomplete, or at least more nuanced than we once believed, and drawing us onward, gently but irresistibly, into the next layer of this unfolding cosmic mystery. And so, carried forward by that quiet unease, the idea that our home might sit inside an enormous underdensity, we drift naturally toward another puzzle. Because if location matters, if environment shapes what we see, then it should leave traces not only nearby, but also far away, deep in time, back toward the universe when it was young. And, that's where the light of quasars enters the story. Quasars are among the brightest things that have ever existed. That statement alone deserves a pause. These are not galaxies in the usual sense, not collections of billions of stars shining gently together. They are compact, furious engines powered by supermassive black holes, devouring matter and releasing vast torrents of energy. For a brief moment in cosmic history, they can outshine entire galaxies. And, because they are so bright, we can see them across immense distances, back to times when the universe was only a small fraction of its current age. For a long time, quasars fit rather neatly into our theories. They were expected to live in dense environments, crowded regions, places rich in gas and mergers where galaxies collide, funneling material toward their centers and feeding the black holes within. Not just anywhere, but the busiest intersections of the cosmic web. That made sense. Gravity brings matter together, chaos drives growth, and brilliance emerges from abundance. But, when the James Webb Space Telescope began peering deeper into the universe than ever before, something unsettling appeared. Quasars, extraordinarily luminous quasars, were being found in places where, according to our expectations, they should not be. Regions that seemed sparse, regions lacking the surrounding scaffolding of massive galaxies and dense filaments. In some cases, these quasars appeared almost isolated, shining fiercely in relative loneliness. And, that loneliness is the key, because a quasar doesn't just light up by accident. It requires fuel. vast quantities of gas. And gas, in the early universe, was supposed to trace the densest structures. So when we see a blazing quasar without a rich environment around it, we are forced to ask a difficult question. Where did the fuel come from? At first, there is always the temptation to doubt the observation. Or perhaps the surrounding galaxies are there, just too faint to detect. Perhaps dust hides them. Perhaps our models of early galaxy formation are incomplete. And, all of those are reasonable possibilities. Science thrives on skepticism. But as the data accumulate, as different observations point in the same direction, the discomfort grows. Because it's not just one quasar, it's a population, a pattern. And patterns, you see, are where the universe speaks most clearly. These early quasars appear not just bright, but astonishingly mature. Their black holes are massive, far more massive than we would expect given the short time available for growth since the Big Bang. That alone was already a challenge. How do you grow a billion solar mass black hole so quickly? Add to that the apparent lack of dense surroundings, and the puzzle deepens. And, here's where the idea of voids quietly returns. If large-scale underdensities exist, if regions of space are less crowded but still connected to the broader cosmic web, then perhaps gas can flow along filaments into isolated systems more efficiently than we once thought. Perhaps the absence of nearby competitors allows material to fall inward more cleanly, more directly. It's not that emptiness starves growth. It might paradoxically enable it. That inversion of intuition is deeply unsettling and deeply beautiful at the same time. We tend to associate richness with abundance, success with crowding. But the universe often works differently. Sometimes isolation is exactly what allows something extreme to form. And, consider this. In a dense region, galaxies collide frequently. Those collisions can trigger star formation, but they can also disrupt delicate inflows of gas. Feedback from stars and black holes can blow material away. In a quieter region, fewer disturbances mean smoother accretion, less chaos, more sustained growth. And that might be the environment a young quasar needs. Not just out there, you see, but also in here, in our theoretical frameworks, in the assumptions we've carried forward for decades. Perhaps the early universe was more varied, more environmentally diverse than our simplified models suggest. And, this matters because quasars are not just curiosities. They are probes. Their light carries information across billions of years. It tells us about the state of the intergalactic medium, about how matter clustered, about how quickly structures formed. When quasars behave unexpectedly, it's a sign that something in our picture needs adjustment. We might be underestimating the role of large-scale structure at early times. We might be assuming too much uniformity, too much smoothness. The cosmic web, after all, begins forming very early. Tiny fluctuations grow quickly. Voids, filaments, and clusters do not appear suddenly at late times. They are seeded almost immediately after the Big Bang. So, if void-like regions existed even in the young universe, then the presence of luminous quasars in seemingly sparse environments becomes less shocking. Still surprising, yes, but no longer inexplicable. Instead, they become signposts, pointing toward a universe that was structured earlier and more dramatically than we once believed. And, well, there is something almost philosophical here. We look back in time, searching for the origins of complexity, and we expect order to arise gradually, uniformly. But the universe may prefer contrast, peaks and valleys, extremes existing side by side. brightness next to darkness, density next to emptiness. And that theme echoes uncomfortably with the idea that our own cosmic neighborhood might be unusual. If we live in a large underdensity now, perhaps we are seeing the descendants of early environments that were already distinct. The universe remembers its beginnings. Structure carries memory. And, it's worth pausing to appreciate just how radical this shift is. The standard picture of cosmology is extraordinarily successful. It explains the cosmic microwave background, the large-scale distribution of galaxies, the overall expansion history of the universe. But it relies on averages. It smooths over extremes. And quasars, especially lonely ones, live at the extremes. They remind us that averages are not the whole story, that the universe is not just statistically elegant, but also locally surprising. And, when you place these observations alongside the idea of the KBC void, something interesting happens. Two independent anomalies begin to resonate. A local underdensity that may affect expansion measurements, and early, isolated quasars that challenge models of structure formation. On their own, each could be dismissed as a fluke. Together, they hint at a deeper pattern. That pattern suggests that large-scale inhomogeneities matter more than we have allowed for. That where you are, and when you are, changes what the universe looks like. And, of course, none of this means our theories are wrong in a catastrophic sense. It means they may be incomplete, like a map drawn with broad strokes that misses the fine details of terrain. Mountains flattened, valleys smoothed. Useful for navigation, but misleading if you want to understand the landscape intimately. We grow older, clocks tick, theories evolve. Science is not static. It adapts. And these quasars, shining stubbornly in unexpected places, are forcing us to adapt again. And, perhaps the most humbling aspect of all is this. The light from these quasars began its journey long before the Earth existed, long before the Sun formed. It has crossed a universe that was changing, expanding, developing structure. And only now, only here, does it end its journey in our detectors, asking us, gently but persistently, to rethink our assumptions. So, as we absorb these clues from the distant past, we find ourselves standing at the threshold of a much more immediate problem. Because if environment affects growth, and if local underdensities affect expansion, then our measurements of the universe today may not all be telling the same story. And indeed, when we compare different ways of measuring how fast the universe is expanding, they do not agree. And, that disagreement is not small. It is precise, persistent, and deeply troubling. A tension, not just in numbers, but in our understanding. A tension that has come to be known as one of the most serious challenges in modern cosmology, and which draws us inevitably toward the question of why two carefully measured views of the same universe might describe expansions that simply do not match. And so we arrive at a moment where the universe seems to hesitate, not in its expansion, not in its relentless stretching of space, but in the stories it tells us about itself. Because when we try to measure how fast the universe is growing, when we try to pin down that single number that describes the rhythm of cosmic expansion, the answers do not agree. And, that disagreement is quiet, precise, and deeply unsettling. This is what we call the Hubble tension. And, the word tension is chosen carefully. It's not a catastrophic contradiction. It's not chaos. It's a persistent strain, like a note slightly out of tune that refuses to resolve. Two ways of measuring the same thing, done with extraordinary care, extraordinary sophistication, give answers that simply do not line up. On the one hand, we have a view of the universe as it was when it was very young. We look at the faint afterglow of the Big Bang, the cosmic microwave background, a bath of ancient light that fills all of space. This light was released when the universe was only a few 100,000 years old, when it first became transparent. It carries an imprint of the early universe, frozen into its tiny temperature variations. And, from that ancient pattern, from those subtle ripples, we can infer the entire history of cosmic expansion, not directly measured, but reconstructed. A model extrapolated forward in time using the laws of physics we believe to be correct. When we do that, we arrive at a value for the expansion rate today that is calm, measured, and lower than what we see nearby. Roughly 67 kilometers per second per megaparsec, give or take. On the other hand, we have the nearby universe. Galaxies close enough for us to measure their distances directly, step by step. We use stars whose brightness we understand, Cepheid variables, and stellar explosions, supernovae, as cosmic mile markers. This distance ladder is painstakingly built, rung by rung, each step calibrated with care. And, when we measure how fast these nearby galaxies are moving away from us, the expansion appears faster. Not dramatically faster, but enough to matter. Around 73 kilometers per second per megaparsec. And that gap between 67 and 73 may sound small, but in cosmology it is enormous. So, we are faced with two universes, not just two numbers, but two narratives. One where the universe expands at a certain rate, inferred from its earliest light. Another where it expands faster, measured directly in the local cosmos. And both methods are exquisitely precise. Both have been checked and rechecked. Errors have been hunted down, corrected, minimized. And yet, the tension remains. And, this is why some have called it a crisis. Not because everything is falling apart, but because the foundations are being quietly questioned. When two trusted tools disagree, the problem may lie not in the tools, but in the assumptions that connect them. And, one of those assumptions is homogeneity. The idea that, on large scales, the universe looks the same everywhere. That our local region is a fair sample of the whole. That when we measure nearby expansion, we are measuring the global expansion. But what if that assumption is slightly wrong? It's not that the universe is wildly different from place to place. It's not chaos. It's subtle, gentle, a matter of degrees. But subtle effects can accumulate. And if we live in an underdense region, a void, then the local expansion of space would be faster than average. Galaxies around us would appear to recede more quickly, not because the universe as a whole is expanding faster, but because our neighborhood is emptier. And, this is where the earlier pieces of the story begin to align. The idea of the KBC void. The possibility that our cosmic address is not typical. The observation that galaxy density increases as we look farther out. These are not isolated curiosities anymore. They become potential explanations. It's not that the cosmic microwave background is wrong. It's not that nearby measurements are flawed. It's that they may be measuring different things. One measures the universe on the largest possible scales, averaged over everything. The other measures the universe from inside a particular environment. It's not just out there, you see. It's in here, in the space we inhabit, in the gravitational landscape that surrounds us. And, imagine standing at the bottom of a shallow valley. From where you stand, the horizon slopes gently upward in all directions. If you tried to infer the shape of the entire landscape based only on your immediate surroundings, you might conclude that the whole world is rising. But step back far enough, and you see the valley for what it is, a local dip in a much larger terrain. So, the Hubble tension could be telling us that we are standing in a cosmic valley, a void, a region where matter is sparse, gravity is weaker, and expansion runs slightly ahead of schedule. And, this idea has a powerful appeal because it does not require exotic new physics, no mysterious particles, no rewriting of gravity itself, just an acknowledgement that structure matters, that the universe is not perfectly smooth, and that those imperfections have consequences. But, it's also controversial, because the void required to explain the full tension would have to be very large, larger than most voids we observe, rare, uncommon. And that raises uncomfortable questions about probability, about whether it is reasonable to believe we live in such a place. And, yet rare does not mean impossible. The universe is vast, almost unimaginably vast. And in a universe that large, even unlikely configurations will exist somewhere. The question becomes whether the evidence points to us being in one of those places. And, this is where statistical analyses enter the conversation. When models that include a local underdensity are compared to models that assume perfect uniformity, the fit to the data can improve dramatically. In some analyses published around 2025, the improvement is not marginal. It is overwhelming, orders of magnitude more likely. And that kind of result cannot be ignored. But even here, caution is essential. Statistics can mislead if the assumptions are wrong. Models can be tuned. Data can be interpreted in different ways. And science advances not by declaring victory, but by probing weaknesses. And, still, the persistence of the Hubble tension is telling us something. It has survived years of scrutiny. It has not faded as data improved. If anything, it has sharpened. And that suggests it is not a mistake, but a clue. We are being invited to reconsider the relationship between local measurements and global truths, to ask whether our cosmic perspective is subtly biased by where we happen to be. And, there is something deeply human about this. We are always trying to understand the whole from where we stand, whether it's society, history, or the universe itself. And we are always at risk of mistaking our local experience for the universal rule. The Hubble tension is the universe gently reminding us of that. And, if local structure can influence expansion measurements, then it must also influence motion. Galaxies do not just drift apart smoothly. They move through a gravitational landscape shaped by clusters, filaments, and voids. If we live near the center of an underdensity, matter around us will be flowing outward, away from the void, toward denser regions beyond. That flow should be detectable, a coherent motion of galaxies on large scales, not random, but directed, a bulk flow. And indeed, such motions have been observed. And, that observation pulls us naturally toward the next layer of the story. Because if voids can shape expansion rates, and if they can influence the large-scale motion of galaxies, then we are not just passengers in an expanding universe. We are embedded in a dynamic cosmic current. And, whether it all fits together perfectly or not, whether the void explanation survives every test or eventually gives way to something deeper, one thing is already clear. The universe is more subtle than our simplest models. It has texture, it has neighborhoods, it has flows and gradients that matter. And, as we follow those flows, as we trace the motion of galaxies across hundreds of millions of light years, we begin to see that our Milky Way is not standing still. It is being carried along, swept by gravitational influences far beyond our local group, moving in concert with thousands of other galaxies, all responding to the invisible architecture of the cosmic web. And that movement, that collective drift, is where this story wants to go next. Toward the great currents of the universe, the mysterious pull of distant superclusters, and the quiet push of emptiness itself, shaping the path we follow through space-time as part of something vastly larger than ourselves. And so, carried along by the idea that motion itself might betray our position in the cosmos, we begin to look more closely at how a void could quietly distort what we measure. Because if the universe around us is underdense, if matter is missing on vast scales, then space itself behaves differently here. Not dramatically, not violently, but subtly. And, subtle effects are often the most dangerous ones because they hide in plain sight. In a region rich with matter, gravity pulls back against expansion. Galaxies tug on one another. Space stretches, yes, but it is restrained, slowed, tempered by mass. In an emptier region, however, that restraint is weaker. There is less gravity to pull inward, and so space expands a little faster. Not because the laws of physics have changed, but because the balance of forces is different. That distinction is crucial. It's not that the universe is expanding faster everywhere. It's that our patch of it might be doing so locally. And if we measure expansion from inside that patch, using nearby galaxies as our reference points, we might be misled. Not lied to, but gently nudged toward a conclusion that reflects our environment rather than the cosmic average. And, imagine floating on a river. The water flows smoothly, steadily. If you drop a leaf nearby, you can measure how fast it moves relative to you. But if you happen to be sitting in a faster current than the one upstream or downstream, your measurement of the river's speed will be biased. You're not wrong about what you see locally. You're just not seeing the whole river. So, if we live inside a void, then the galaxies around us are carried outward more quickly, pushed by the relative absence of matter. Their redshifts increase. Their apparent recession speeds grow. And when we convert those speeds into an expansion rate, we infer a higher value for the Hubble constant. It's not just theory. This effect can be modeled, simulated, calculated within the framework of general relativity. When researchers include a large local underdensity in their models, something remarkable happens. The discrepancy between early universe and late universe measurements begins to shrink, sometimes dramatically. And, in analyses that gained attention around 2025, models incorporating a void like the one suggested by observations around us fit the data astonishingly well. Not just slightly better, orders of magnitude better. In statistical terms, the improvement can be so large that it's hard to ignore. On the order of hundreds of millions times more likely than models assuming perfect uniformity. That kind of result forces you to pause, to breathe, to reconsider what you thought you knew. And, this does not mean the void explanation is proven. Science rarely offers that kind of closure, but it does mean the idea has teeth. It can bite into real data and leave a mark. It offers a coherent narrative that links galaxy counts, local expansion measurements, and large-scale structure into a single picture. Not just this anomaly, but also that one. Not just here, but also there. And, the elegance of it is appealing. We don't need to invent new forces or particles. We don't need to discard the standard model of cosmology. We simply need to accept that the universe is not perfectly smooth, and that our location within its structure matters. It's not a radical claim when you think about it. We already accept that living inside a galaxy affects what we see. Dust obscures our view. Motion affects our measurements. Why should living inside a void be any different? And, yet there is resistance. And that resistance is understandable. The Copernican principle, the idea that we are not in a special place, is deeply woven into modern cosmology. It has served us well. It guards against arrogance, against the temptation to see ourselves as central or privileged. But perhaps, we have misunderstood what that principle truly demands. It does not say that every location must be identical. It says that the laws of physics are the same everywhere. And they are. Gravity behaves the same in voids as it does in clusters. Light travels the same. Time ticks the same. What differs is the environment. And environments matter. And, when critics argue that a void large enough to explain the Hubble tension is too improbable, they are making a statistical statement. But statistics depend on assumptions, on how you define typical, on what you consider likely in a universe as vast as ours. And, with billions upon billions of cubic megaparsecs to choose from, rarity becomes a slippery concept. We should be careful not to confuse discomfort with impossibility. And, there is another subtle point here. Even if the void does not explain the entire Hubble tension, it could explain part of it, a fraction. And that alone would be significant, because it would mean that some of the discrepancy arises not from new physics, but from cosmic geography. And that realization would reshape how we interpret cosmological data. It would remind us that measurements are not abstract. They are made from somewhere. And, think about how extraordinary it is that we are even having this conversation. We are tiny beings on a small planet, orbiting an average star, in a galaxy that may itself sit in an underdense region of a universe nearly 14 billion years old. And yet, we are sensitive enough, clever enough, curious enough to detect a mismatch of a few kilometers per second per megaparsec and wonder what it means. That is awe-inspiring. And, as this picture develops, as voids move from the margins of cosmology to its center, another consequence emerges. If expansion is faster inside a void, then matter around us must be flowing outward. Galaxies are not just receding due to cosmic expansion. They are also moving relative to the average frame of the universe, responding to gravitational gradients. This motion should have a direction, a coherence, a sense of flow. And indeed, observations suggest that our local group of galaxies, and many beyond it, are drifting together through space at hundreds of thousands of miles per hour relative to the cosmic background. And, that flow is not random. It points away from emptiness and toward mass, toward enormous concentrations of galaxies far beyond our local neighborhood, toward structures so massive they warp space-time on scales difficult to imagine. So, the void does not just change how fast the universe appears to expand, it changes how we move through it. It places us on a gentle slope, sliding through a gravitational landscape shaped by both presence and absence. And, that motion has been given a name. Bulk flow. A collective drift of galaxies, including our own, carried by the uneven distribution of matter on the largest scales. And, as we follow that motion, as we trace where it leads and what drives it, we step into the next chapter of this story. A chapter about cosmic currents, about immense attractors and repellers, about how emptiness itself can push as effectively as mass can pull. And, If voids can bias our measurements and guide our motion, then they are not passive backdrops. They are active players, shaping not only what we see, but where we are going. And that realization draws us onward, deeper into the dynamics of the cosmic web, toward the great flows of galaxies and the invisible hands that steer them across the universe. And so, once we accept that emptiness can shape motion, that absence can act almost like a force, we begin to notice something extraordinary about our own journey through the universe. Because the Milky Way is not drifting aimlessly. It is not simply being carried along by the smooth expansion of space. It is moving with purpose, with direction, with a speed that is difficult to ignore. And, when astronomers first measured this motion, they were startled. Our galaxy, along with its neighbors, is traveling through space at roughly 600,000 miles per hour relative to the cosmic background. That number is astonishing. It's far faster than the motions of stars within galaxies, far faster than anything we experience in daily life. And yet, on cosmic scales, it is gentle, almost graceful. This collective motion is known as bulk flow, and, the name captures something important. It's not random jitter. It's not individual galaxies darting about independently. It's thousands of galaxies moving together, like leaves carried along by a vast, invisible current. And, how do we know this? We know because the universe has a reference frame. The cosmic microwave background, that ancient afterglow of the Big Bang, defines a kind of cosmic rest. When we observe it, we see a tiny temperature difference across the sky. One direction slightly warmer, the opposite slightly cooler. That dipole pattern tells us that we are moving relative to this primordial light. And, when we correct for the motion of the Earth around the Sun around the galaxy within the local group, what remains is a motion of the local group itself, a bulk flow, a drift through space that cannot be explained by random chance alone. So, what is pulling us? Or perhaps more accurately, what is pushing us? For a long time, astronomers assumed that this motion must be caused by massive structures ahead of us. Enormous concentrations of galaxies whose gravity tugs everything nearby in their direction. And indeed, there is such a structure. The Shapley supercluster, one of the most massive known concentrations of matter in the nearby universe. And, Shapley is immense. Tens of thousands of galaxies bound together across hundreds of millions of light years. Its gravitational influence is real. It pulls. It bends space-time. It draws matter inward, and it contributes to our motion. But, when researchers modeled the bulk flow using Shapley alone, something didn't quite add up. The direction was slightly off. The magnitude didn't fully match. It was as if something else was at work. Something less obvious. Something harder to see. And, that's when the idea of a repeller entered the conversation. A concept that feels almost counterintuitive at first. A region not defined by mass, but by its absence. A vast underdensity that effectively pushes galaxies away, not by exerting force, but by lacking gravity. This region has been given a name, the dipole repeller, and, it sits roughly opposite the direction of the Shapley supercluster. Not a thing you can point a telescope at, not a cluster blazing with light, but a vast emptiness, shaping motion through its very lack of substance. It's not pulling us, it's letting us go. And, when you include both effects, the pull of Shapley and the push of the dipole repeller, the bulk flow begins to make sense. The direction aligns, the speed matches, the pieces fall into place. That That is a profound moment, because it tells us that voids are not passive. They are not merely gaps between structures. They actively shape the motion of galaxies on the largest scales. It's not just mass that matters. It's the distribution of mass, and the distribution of nothing. And, think about how strange that is. We are used to thinking of gravity as something that pulls, something that attracts. But here, the absence of gravity creates a gradient, a slope in the gravitational landscape that galaxies slide down, away from emptiness, toward richness. And, this bulk flow is not small. It extends across hundreds of millions of light years. It involves thousands of galaxies. It is one of the clearest demonstrations that the universe is not static on large scales, not even in a relative sense. Everything is moving, flowing, responding to structure. And, the Milky Way is part of that dance. Our galaxy, our stars, our planet, we are all being carried along. We feel none of it, of course. Motion is relative, but the universe keeps careful track. And, this realization ties beautifully back to the idea of the local void. If we live inside an underdense region, then matter around us must be flowing outward. The void expands faster than average. Galaxies move away from its center. That outward flow contributes to the bulk motion we observe. So, the void does not just bias our measurements, it moves us. And, this has subtle consequences. When galaxies move relative to the cosmic background, their velocities add to or subtract from the expansion of space. These peculiar velocities can distort distance measurements. They can introduce noise, or perhaps signal. And if they are coherent over large scales, they can leave imprints that we must account for. And, again, the theme returns. Location matters. Environment matters. The universe is not a featureless stage. It is a landscape, with hills and valleys, currents and flows. Time is not a clock. It's a landscape we travel through. And space, too, is not an empty container. It is shaped, sculpted, dynamic, and, when we trace these flows backward, when we ask where they originate, we are inevitably led deeper into cosmic history. Because the structures that drive bulk flow did not appear overnight. They grew from tiny fluctuations in the early universe, seeds planted almost at the beginning of time. And, that brings us to an even earlier chapter, to a time when sound waves rippled through hot plasma, when matter and radiation were locked together in a delicate dance, when the blueprint of the cosmic web was first laid down. Because if voids today are pushing galaxies around, if they are shaping expansion and motion, then we must ask how they formed in the first place. Were they inevitable? Were they seeded in the earliest moments? Or are they the result of later cosmic evolution? And, the answer lies in subtle patterns imprinted across the universe. Patterns that trace back to the first few 100,000 years. Patterns that still echo today in the distribution of galaxies themselves. And, as we follow those echoes, we find ourselves drifting further back in time, toward the origin of voids, toward the primordial fluctuations that set everything in motion, and toward the realization that even the emptiest regions of space carry the memory of the universe's earliest breath. And so, as we drift backward in time, carried by the motion of galaxies and the quiet push of emptiness, we arrive at a question that feels almost inevitable. If voids today shape expansion and motion, if they push galaxies and bias our measurements, then where did they come from? When did the universe first decide that some regions would become rich and crowded, while others would grow vast and empty? And, the answer does not lie in the recent universe. It lies deep in the past. Very deep. Back to a time when the universe was hot, dense, and young, when everything we now see was compressed into a state so extreme that our everyday intuitions simply fail. In those earliest moments, the universe was not yet divided into galaxies or clusters or voids. It was a nearly uniform sea of energy and matter, glowing, opaque, restless. But nearly uniform does not mean perfectly uniform. And that tiny imperfection is everything. Because in the first fractions of a second, during a period we call inflation, space itself expanded at a breathtaking rate. And in that expansion, quantum fluctuations, minuscule variations that flicker in and out of existence even in empty space, were stretched to cosmic scales. Tiny differences in density were frozen into the fabric of space-time. It is difficult to overstate how small these differences were. 1 part in 100,000. Barely anything at all. And yet, gravity is patient. Gravity does not need large beginnings. It only needs time. And, after inflation ended, the universe settled into a slower expansion. Matter and radiation were still tightly coupled, locked together in a hot plasma. Light could not travel freely. Sound, however, could. Pressure waves rippled through this primordial soup, driven by the competition between gravity pulling matter inward and radiation pressure pushing it outward. These ripples are known as baryon acoustic oscillations. And, the name sounds technical, but the idea is beautifully simple. They are sound waves in the early universe, cosmic echoes from a time when everything was compressed into a glowing fog. And, these waves traveled outward from tiny overdensities, like ripples on a pond. They carried matter with them, pushing it outward until the universe cooled enough for light to decouple from matter. At that moment, the ripples froze, the sound stopped, and the pattern was locked in. That pattern became the blueprint of structure. Some regions ended up slightly denser than average, others slightly emptier. And those differences, though small, were enough. Over billions of years, gravity amplified them. Dense regions grew denser. Empty regions lost matter to their surroundings. And slowly, inevitably, voids emerged. So, voids are not late accidents. They are not gaps punched into an otherwise smooth universe. They are part of the original design, written into the cosmos almost from the beginning. And, this is why the existence of vast voids does not violate our theories. Quite the opposite. In a universe born from inflation, seeded with quantum fluctuations, a wide range of structures is expected. Filaments, clusters, walls, and voids of many sizes. Some voids are small, some are enormous, and in a universe as large as ours, the tail of that distribution can extend to truly staggering scales. And, this matters deeply for the idea that we might live inside a very large void, because it means such a region does not require new physics. It does not require special pleading. It is a natural, if rare, outcome of known processes. We must be careful here. Rare does not mean impossible. And cosmology is a science of the possible, not just the probable. And, the cosmic microwave background offers a remarkable confirmation of this story. When we observe it, we see tiny temperature variations across the sky, hotter spots, cooler spots. These are direct imprints of the primordial fluctuations. They tell us how matter was distributed when the universe was only a few 100,000 years old. And, those fluctuations have a statistical character. They follow patterns predicted by inflation. And when we evolve those patterns forward using gravity, they produce a universe remarkably like the one we observe. A cosmic web, a foamy structure, vast voids surrounded by luminous filaments. It's not just theory. It's a quantitative success. And, what's extraordinary is that voids preserve memory. Because they are underdense, they evolve more gently. They experience fewer mergers, fewer violent events. In some sense, they are quieter places. And that quietness means they retain information about the early universe more cleanly than crowded regions do. So, studying voids is like reading an ancient manuscript that has been handled less, smudged less, altered less by time. They are archives of cosmic history. And, this is why modern cosmology has begun to take voids seriously, not as empty curiosities, but as precision tools. Their shapes, sizes, and distributions can tell us about inflation, about dark energy, about gravity itself. And, when researchers simulate universes with slightly different initial conditions, slightly different physics, the properties of voids change in subtle but measurable ways. That makes them powerful tests of our models. And, here again, the theme returns. The universe is not just a collection of objects. It is a process, a story unfolding over time. And voids are chapters in that story, not footnotes. It's not just out there, you see. It's in here. In the equations we write. In the assumptions we make about smoothness and typicality. And, if voids are seated in the earliest moments, then the existence of a very large void around us does not require coincidence. It requires only that the initial fluctuations allowed it. And given enough volume, given enough cosmic real estate, such regions will exist. The question then shifts. Not whether voids can form, but how they influence everything else. And, because once a void forms, it begins to shape its surroundings. Matter flows out of it. Filaments sharpen around its edges. Galaxies on its boundary feel a gentle but persistent push. Over time, the void grows. It becomes emptier, more influential. And, dark energy only amplifies this process. As the universe expands and dark energy comes to dominate, underdense regions expand faster than dense ones. Voids stretch. They accelerate away from their surroundings. So, voids are not just relics of the past. They are agents of the future. And, this perspective reframes the entire cosmic narrative. Instead of thinking of structure as something that builds upward, from small to large, we can also think of it as something that evacuates. Matter drains from some regions and piles up in others. Growth through loss. And, there is something quietly poetic about that. That emptiness itself grows. That absence can have a history. That the largest things in the universe may be defined not by what they contain, but by what they lack. And, as we look around our own cosmic neighborhood, we begin to see how this history might have shaped us. A galaxy living in or near a void would experience fewer violent interactions, fewer mergers, a calmer evolutionary path. And, that calm has consequences. It affects star formation, gas retention, morphology, the very character of galaxies. So, if voids were present early, and if they have been shaping environments ever since, then they may have quietly influenced where and how galaxies like the Milky Way formed. And, this thought brings us gently, almost inevitably, toward a more intimate question. Not just where voids come from, but what it is like to live inside one. What kind of environment does a void provide for galaxies, for stars, for planets, for life itself? Because the universe does not just ask how things form, it also asks how they endure. And, as we move from the grand origins of voids to their local consequences, from primordial fluctuations to galactic neighborhoods, we begin to see that emptiness is not hostile. It can be gentle, protective, stable. And that realization opens the door to the next part of the story. A story about quiet galaxies, long-lived spiral arms, and the possibility that the very emptiness around us may have given us the time and stability needed to exist at all. And so, having traced the origin of voids back to the very first whispers of the universe, we arrive somewhere unexpectedly intimate, somewhere quieter. Because once you understand how voids form, how they grow, how they shape motion and expansion, a gentler question begins to surface. Not about equations or measurements, but about environments, about what it is actually like to live inside emptiness. And, this is where the story turns inward. Galaxies that reside in voids live very different lives from those crowded into clusters. Not dramatically different in appearance at first glance, but different in temperament, in history, in rhythm. In dense regions, galaxies are constantly interacting. They collide, they merge, they tear gas from one another. Star formation flares violently and then shuts down. Black holes awaken, blow out surrounding material and quench further growth. But in voids, things are calmer, much calmer. Galaxies drift farther apart. Encounters are rare. Major mergers happen less often. And because of that, galaxies tend to hold on to their gas. They are not stripped or harassed as frequently. Their star formation proceeds slowly, steadily, over billions of years, rather than in brief, catastrophic bursts. And, this matters, because stars form from gas, and gas is the raw material of complexity. The longer a galaxy can keep its gas, the longer it can continue forming stars. The longer it can remain dynamically stable. So, void galaxies often retain their spiral shapes. Their disks remain thin, their arms graceful. They do not get scrambled as often by violent interactions. They age gently. And, when astronomers study the Milky Way and its nearest neighbor, Andromeda, they notice something striking. Both are large spiral galaxies. Both still have significant gas. Both are forming stars at a moderate, sustained rate. And both have avoided major disruptive mergers for a very long time. That combination is not typical of galaxies in dense clusters. It's not just coincidence. It's environment. And, galaxies like ours look remarkably similar to galaxies found in underdense regions. Their histories align. Their morphologies align. Their calmness aligns. And, this does not mean voids are empty wastelands. Far from it. They contain galaxies, stars, planets, but they offer space, time, stability. And, when you begin to think about life, about chemistry complex enough to replicate and evolve, stability becomes precious. Planets require long-lived stars. Biospheres require billions of years without catastrophic disruption. Too much violence too often, and complexity resets before it can deepen. We often think of life as something that thrives on abundance, on richness, on activity. But perhaps it also needs quiet. Perhaps it needs a cosmic suburb rather than a crowded downtown. And, this is not speculation without grounding. Regions of high galaxy density experience more energetic radiation, more supernovae, more active galactic nuclei. Those events flood space with high-energy particles that can strip atmospheres and sterilize surfaces. In a void, those events are rarer. Farther away, their effects diluted by distance. And, This does not guarantee life, of course. Nothing does. But it tilts the balance. It creates an environment where complexity is allowed to persist long enough to explore its own possibilities. It's not that life requires emptiness. It's that emptiness may give life time. And, when you realize that, the idea that we might live inside a large void takes on a different emotional tone. It is no longer just a technical explanation for cosmological tensions. It becomes part of our own story. Not just out there, you see. It's in here, in the conditions that allowed us to exist at all. We grow older, clocks tick, civilizations rise and fall. All of it happens within a galaxy that has been spared the worst excesses of cosmic violence. A galaxy that has lived a relatively peaceful life in a relatively quiet neighborhood on the edge of vast emptiness. And, there is something profoundly humbling about that. That our existence may depend not only on physical laws, but on where we happen to be within the grand structure those laws produce. And, this does not mean the universe is designed for us. There is no intention implied, only consequence. The universe does not care whether galaxies are crowded or isolated, but we do, because we live in one of them. And, in this sense, voids are not failures of structure. They are features. They are the spaces that allow gentler histories to unfold. And, yet even this quiet is temporary, because the universe is changing. Dark energy, that mysterious driver of accelerated expansion, is becoming ever more dominant. As time passes, it stretches space faster and faster, and underdense regions respond most dramatically. Voids expand more rapidly than dense regions. Their interiors thin out further. Galaxies within them drift farther apart. Over immense spans of time, the isolation deepens. So, the very environment that may have nurtured long-term stability is also an early preview of the universe's distant future. And, imagine that future. Galaxies outside the local group receding beyond the horizon. One by one, the lights of the cosmic web fading from view, filaments dissolving into darkness, clusters slipping away. What remains is something very much like a void, vast, quiet, empty. And, in that future, observers like us would see a universe almost devoid of structure, a lonely island of galaxies surrounded by darkness. They might never know the richness that once existed beyond their horizon. And, this thought loops back on itself, because in some sense, we may already be living in an early version of that future, a gentle isolation that allows reflection, observation, memory, and, voids, then, are not just places in space. They are stages in time. They show us where the universe has been and where it is going. And, as we look ahead, as we imagine a cosmos increasingly dominated by dark energy, the role of voids only grows. They expand faster. They empty more completely. They come to dominate not just volume, but experience. And, this brings us naturally to the next question. Not about how voids formed or how they shape life now, but about what they become. About the ultimate fate of a universe where emptiness accelerates and structure slowly slips away. Because if voids are growing, if darkness is spreading, then the quiet that once nurtured complexity may eventually erase our view of the universe altogether. And, that is where this journey leads next. Toward the far future. Toward a universe stretched thin by dark energy. Toward a time when voids are no longer just regions between things, but the defining feature of everything we can see. And so, standing at the edge of that quiet realization, that emptiness may both nurture life and foreshadow its isolation, we are drawn inevitably toward the far future. Because the universe is not finished. It is not settling down. It is accelerating. And, that acceleration changes everything. At the heart of this change is dark energy, a name that sounds mysterious, almost evasive, because in truth we do not yet know what it is. We know it exists because of what it does. It stretches space. It pushes galaxies apart faster and faster as time goes on. And unlike matter or radiation, it does not dilute as the universe expands. It remains steady, persistent, and, as dark energy comes to dominate, its influence is felt most strongly in the emptiest places. Voids. Regions already low in matter respond more dramatically. With less gravity to resist the expansion, they stretch faster than average. Their interiors thin out. Their boundaries recede. So, the future of the universe belongs to voids. Not just by volume, which is already true, but by experience. What observers will see. What remains visible. What endures within the horizon of knowledge. And, imagine the universe tens of billions of years from now. Galaxies beyond our local group drift away, faster and faster, until their light can no longer reach us. One by one, they cross the cosmic horizon, not exploding, not vanishing dramatically, just fading, quietly slipping beyond reach. And, eventually, the great filaments of the cosmic web will no longer be visible from here. The Shapley supercluster. Distant clusters. Even nearby groups beyond our gravitationally bound neighborhood will disappear. The universe will look smaller, emptier, simpler. It will look like a void. And, in that future, the local group of galaxies will remain bound. Gravity still wins on small scales. The Milky Way and Andromeda will merge. Stars will continue to shine. Planets may still orbit. But the larger universe will be gone from view. Not gone in reality. Gone from experience. And, this is a profound thought, because it means that our current view of the universe is temporary. The rich tapestry of galaxies, the cosmic web stretching across billions of light years, is something we are fortunate to witness now. We grow older, clocks tick, civilizations rise and fall, and yet the window through which the universe can be seen is slowly closing. And, in a dark, energy-dominated future, observers living in isolated island galaxies may never know that the universe was once filled with structure. They may never detect the cosmic microwave background. They may never infer a Big Bang. Their universe will appear static, lonely, finite. And, from their perspective, the universe will look eternal and unchanging. A single galaxy surrounded by darkness. That is not speculation. It is a consequence of the laws we observe today. And, this is where voids become more than just regions of space. They become a metaphor for destiny. A preview of what the universe becomes when expansion outruns connection. And, there is something quietly unsettling about that. Because knowledge itself depends on horizons, on access to information, on light reaching us from distant places. As horizons shrink, so too does what can be known. It's not that the universe becomes simpler, it's that our access to its complexity diminishes. And, this casts our present moment in a new light. We live at a time when the universe is old enough to have formed rich structure, but young enough that we can still see it. A fleeting balance. And, voids help us understand that balance. They show us how underdensity accelerates expansion, how emptiness grows, how isolation deepens. And, In this sense, the void we may inhabit today is not an anomaly. It is an early chapter in a story that ends with near total isolation. So, when we talk about the KBC void, about local underdensities and cosmic flows, we are not just diagnosing a present-day puzzle. We are glimpsing the trajectory of the universe itself. And, this does not make the future bleak. It makes it precious. Because meaning is not erased by finitude. If anything, it is sharpened by it. And, there is also humility here. We often imagine that future civilizations will know more than we do. And they will, in many ways. But in cosmology, they may know less. They may lack the evidence we now possess. The sky itself will have forgotten its past. And, that realization carries a quiet responsibility. To observe, to record, to understand now, while the universe is still generous with its clues. And, voids remind us of that urgency. They show us how structure dissolves, how horizons close, how the universe simplifies with time. And, yet even as the future stretches toward emptiness, questions remain. Dark energy itself is still mysterious. Is it constant? Does it evolve? Will it always dominate? Or will something unexpected occur? Whether it exists as a simple cosmological constant or something deeper is still unknown. And, this uncertainty keeps the story open. The universe has surprised us before. It may do so again. And, which brings us to the final layer of this journey. Because even if voids explain many things, even if they help us reconcile tensions and flows and futures, they may not be the whole story. There are still gaps, still inconsistencies, still whispers that something is missing from our picture. And, to understand that, we must look back at our most trusted model of the cosmos, examine where it succeeds, where it strains, and ask whether voids are the answer, or merely a signpost pointing toward something deeper. And, that question waits patiently at the edge of everything we have discussed, inviting us to step just a little further into the unfinished parts of our understanding, where certainty fades, curiosity sharpens, and the universe reminds us that even now, even here, we are still only beginning to listen. And so, after following voids from their birth in the earliest moments to their dominance in the far future, we are left standing before an unfinished picture. Not broken, not wrong, but incomplete. And, that is often where science becomes most interesting. Because the framework that holds most of modern cosmology together, the model we rely on to describe the universe from its first breath to its accelerating expansion, has been remarkably successful. We call it Lambda CDM, a universe filled with ordinary matter, dark energy, expanding from a hot beginning, growing structure through gravity. It explains the cosmic microwave background. It predicts the large-scale distribution of galaxies. It gets so many things right. And yet, there are tensions, small cracks, persistent anomalies, the Hubble tension, unexpected bulk flows, quasars where they should not be, and perhaps the possibility that we live in a very large underdensity. It's not that the model fails, it's that it may be stretched. And, voids enter this story as both a solution and a challenge. They can ease some tensions without invoking exotic new physics. They remind us that environment matters, that cosmic averages do not always describe local reality, but, they do not answer everything. Because even if voids explain part of the discrepancy in expansion rates, questions remain. Why do the early universe and late universe measurements still disagree so precisely? Why do some anomalies persist even when local structure is accounted for? Whether voids are the cause or merely a contributing factor is still uncertain. And, this uncertainty opens the door to deeper possibilities. Some physicists wonder whether gravity itself behaves differently on the largest scales. Modified gravity theories attempt to explain cosmic acceleration without dark energy. Others consider additional particles, sterile neutrinos, subtle changes in the energy content of the early universe. Each idea carries consequences. Each must pass rigorous tests. And, what is striking is that many of these alternatives affect voids in particularly sensitive ways. Void shapes, void growth rates, void dynamics. Because voids are low-density laboratories, places where gravity operates gently, deviations from standard physics can stand out more clearly. So, voids become testing grounds, not just explanations, but probes. And, this reframes the question entirely. It's not simply whether we live in a void. It's whether studying voids can tell us something fundamental about gravity, about dark energy, about the laws that govern spacetime itself. It's not just out there, you see. It's in here, in our equations, in our assumptions, in the quiet places where theories strain. And, there is also a philosophical layer that is impossible to ignore. The Copernican principle has guided cosmology for centuries. The idea that we are not special, not central, not privileged. Living in a large void feels uncomfortable because it brushes against that instinct. And yet, perhaps we have misunderstood what non-special truly means. It does not mean identical. It does not mean average in every respect. It means governed by the same laws. And those laws allow variety. We live on one planet among billions, around one star among hundreds of billions, in one galaxy among trillions. But that does not mean every star, every galaxy, every region must be the same. Diversity is not privilege. It is inevitability. And, perhaps the deeper lesson is humility. That our perspective is always partial. That when we look out at the universe, we are seeing it from somewhere. Somewhere with its own history, its own structure, its own biases. Science advances by learning to recognize those biases. And, this is why the question of voids is so powerful. It forces us to confront the relationship between observer and cosmos, between local measurement and global truth. And, as new surveys map the universe with unprecedented precision, as future telescopes trace billions of galaxies and millions of voids, we will refine this picture. We will learn whether the KBC void is exceptional or part of a broader pattern, whether the Hubble tension softens or deepens, whether new physics waits beyond the horizon. And, until then, the picture remains open. Not closed, not settled. And that openness is not a weakness. It is the engine of discovery. We grow older, clocks tick, theories evolve. The universe does not rush to give up its secrets. It invites patience, curiosity, wonder, and, perhaps the most important realization of all is this. Whether voids explain everything or only part of the story, they have already changed how we think. They have shifted our attention from what is there to what is not, from matter to absence, from brightness to darkness. And, in doing so, they have reminded us that emptiness is not nothing. It has structure, it has influence, it has a story. And, as we stand here, on a small planet, in a quiet galaxy, inside a vast and possibly underdense region of an expanding universe, we are not diminished by that realization. We are enlarged by it. Because to understand where we are is to understand who we are. Not in a cosmic sense of importance, but in a sense of belonging. We are part of a universe that is subtle, textured, unfinished. A universe that still has questions. And that is a universe worth listening to. And, having followed this thread from foamy structure to empty futures, from early fluctuations to present tensions, the story does not truly end here. It circles back. Back to the night sky. Back to observation. Back to the simple act of looking up and asking, quietly and honestly, where exactly we are standing in all of this. And, because the more carefully we listen, the more the universe seems to whisper the same invitation. To keep questioning, to keep measuring, to keep wondering, and to accept that even now, even after all we have learned, we may still be living inside a mystery far larger and far emptier than we ever imagined. And so we come to the end of this journey, not with a final answer, but with a deeper sense of where we are. Because when you step back and look at the whole picture, from the foamy structure of the cosmic web to the lonely quasars, from the tension in the expansion of space to the quiet pull and push of voids, a subtle truth begins to emerge. The universe is not just something happening out there. It is something we are inside of. We have seen that space is not empty in the way we once imagined. It is shaped, textured, alive with structure. Vast filaments of galaxies trace invisible paths of gravity, while enormous voids dominate the volume of the cosmos. These voids are not mistakes. They are not absences waiting to be filled. They are natural outcomes of a universe that began with tiny imperfections and had the patience of billions of years to amplify them. And, when we consider the possibility that our own galaxy may reside within one of these immense cosmic hollows, the implications ripple outward. The Hubble tension may no longer be just a problem of measurement, but a clue about perspective. The bulk flow of galaxies may not be random motion, but a response to a landscape shaped as much by emptiness as by mass. Even the calm, long-lived nature of the Milky Way may be tied to the quiet environment in which it evolved. It's not that we are special in a cosmic sense. It's not that the universe was arranged for us. It's that structure allows variation, and variation allows stories to unfold in different ways. We grow older, clocks tick, stars are born and die, all within a universe that is expanding, stretching, and slowly isolating itself under the influence of dark energy. In the far future, the cosmos will look emptier than it does today. Most galaxies will slip beyond our horizon. What remains will feel like a void made absolute. And yet, here we are, at a moment when the universe is still generous enough to show us its depth. And, that may be the most important insight of all. Science, at its heart, is not only about equations and models. It is about orientation, about knowing where you stand when you ask a question. When we ask how fast the universe is expanding, or how structure formed, or why galaxies move the way they do, we are also asking something quieter. Where are we in all of this? Perhaps we live in a vast cosmic void. Perhaps we do not. The evidence is still unfolding, the debate still alive. But even raising the question has already changed how we see the universe. It has reminded us that emptiness matters, that absence can shape motion, time, and destiny. And, there is something profoundly beautiful in that. That a universe so vast, so ancient, so indifferent to individual lives can still be understood piece by minds like ours. minds that emerged on a small planet, orbiting a quiet star, in a galaxy drifting through an ocean of space. We live in a universe that is mostly empty, and yet that emptiness has allowed structure, complexity, and consciousness to arise. It has given us the silence needed to listen. So when you look up at the night sky, perhaps you are not staring into nothingness. Perhaps you're looking into a carefully sculpted landscape where even the voids have meaning. And in that landscape, small as we are, we have found a place from which the universe can, at least for a moment, come to know itself.